Now visualize this situation. Your friend asks you for an assistance. In a few days, she'll be hosting some guests in her house, and she requests that you help her measure out and cook some quantity of rice for her guests. You accept to help her, but next you ask her, what quantity of rice do you want me to cook for your guests? In response, she says, 1 million grains of rice. On hearing that, you shudder. You are surprised. You ask, how can somebody measure out 1 million grains of rice? What it means is that you have to sit down one by one, count 1 million grains of rice before you proceed to cooking the rice. Just think about it. How much time, how much energy do you think will be required to count 1 million grains of rice? The time and energy required are unimaginably high. You can agree with me. You know that that is unthinkable. And then you wish that there is something better you can do to still help your friend. Perhaps he has a reason for insisting that 1 million grains of rice be cooked. And you still want to help her. But you wish that you can get the 1 million grains of rice without having to count the rice one by one. At a point, you remember that people have always chosen to use cups and some other containers of specified quantities of rice to measure rice. Maybe you choose to use cups to measure the rice. If you choose to use the cup to measure rice, the first thing that will come into your mind will be the number of grains of rice that 1 cup will contain, so that you can use cups to measure the 1 million grains of rice required of you. Fortunately, you are told that 1 cup of rice will contain 5,000 grains of rice. You can agree with me that that will be the beginning of the success of this venture. That is, you want to measure 1 million grains of rice without counting the rice one by one. Now you have been told that 5,000 grains of rice make up 1 cup. The implication is that once you scoop 1 cup of rice, you have scooped 5,000 grains of rice. Next, you ask yourself, if 1 cup of rice contains 5,000 grains of rice, how many cups, therefore, will make up the 1 million grains of rice required? If you work it out, you will arrive at 200 cups of rice. Then, you go on to measure the rice by scooping 200 cups of rice. Imagine counting the rice one by one up to 1 billion and scooping 200 cups of rice. Whether you count the rice one by one or you scoop in cups, you are to bring out 1 million grains of rice for cooking. Which of these two takes less time and takes less energy? It is indisputable that scooping it in cups is much easier and takes less time. Therefore, you have used a bundle of rice to measure out a specified number of grains of rice. 1 cup here could be called a bundle of rice, while the 5,000 grains of rice in a cup may be called rice entities or units of rice or grains of rice. So here, you have used a cup, which is a bundle, to measure units, which are grains of rice. Use of bundles to measure units takes less time and energy. The use of bundles to measure units is called algebra. On that note, I say, welcome to the world of algebra. This topic is entitled Fundamentals of Algebra. It is number 4 in my series called Foundations of Mathematics. In it, I seek to explain step by step, section by section, with many examples therein, how algebra has become so important in modern day. Throughout the treatment of this topic, one thing will stand out. What is it? Counting units by means of bundles. Again, I say, welcome to the world of algebra. Please find the proposed content of this lesson. The first objective is getting to know algebra, and that is called Introduction to Algebra. Please join me as I develop step by step, section by section, using examples where necessary to explain the concept of algebra. Again, it is Foundations of Mathematics. This time around, Fundamentals of Algebra. Let's take the first shot. To get to appreciate the emergence of algebra, join me as I count these dots. These dots represent p-naughts. That is, let each dot, like this, represent a p-naught. So look at the p-naughts, all of them. How many p-naughts are there in all? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45 p-naughts. Let me write 45 p-naughts. If I wish to count the time of counting these p-naughts, I can get it by multiplication. We have 1, 2, 3 in a row. That is a column. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 3 in a column times 15. In other words, if I don't want to count these p-naughts one by one as I did before, I can still get it by saying 3 times 15. I hope that is clear. Let me write it. And here it comes. We say alternatively, number of p-naughts is equal to 3 times 15. That is 3 times 15. Shortly, we get the answer as 45 p-naughts. You agree with me that counting these p-naughts one by one takes more time and energy, but doing it this way, 3 times 15, saves us energy and time. If we don't want to say 3 times 15, we can as well say 15 times 3. That is 15 in a row times 3 rows. That will give us 15 times 3. Whichever way, the answer is 45 p-naughts. In more than these two ways, we can get 45 as number of p-naughts. That is, in more than 3 times 15 or 15 times 3, we can get the same 45. Recall that this 3 is number of p-naughts in this column, and this 15 is the number of peanuts in this row. That is 3, 3, 3 times 15. Also, we have 15 times 3 rows. In these two ways, we get 45. Let me stress again that it is possible to get the same 45 by arranging these peanuts differently. We can arrange them differently and still get 45 peanuts by multiplication. Please, notice what happens next. And now, what have you observed? Obviously, the former 45 peanuts are now placed in groups. Group 1, Group 2, Group 3, Group 4, Group 5. So we now have 5 different groups. And when the number of peanuts in each group is the same everywhere, then times 5, it means that will still give us 45 peanuts. First, let us find out whether the number of peanuts in each group is still the same. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 peanuts in this group. Please confirm that in the remaining groups that there are 9 peanuts in each. Certainly, there are 9 peanuts in all the groups. Now, why are we doing this? We're doing it because I said earlier that it is not only by saying 3 times 15 or by saying 15 times 3 that we can also get these 45 peanuts. Don't forget that the first exercise involved counting all the 45 peanuts one by one. But in effort to cut time and space and energy, then we have to resort to grouping them, and the grouping, how to do it, counting 3 in a column times 15 columns, or counting 15 in a row times 3 rows. Now we come with a different method of doing it. This is just one out of numerous other methods we can employ. But one thing is clear. That which is clear is that we are now counting 45 peanuts in groups. Again, look at this arrangement. Each of these boxes contains 9 peanuts. What it means is that the total number of peanuts will be equal to 9 times 5. Let me write that 9 times 5 is equal to 45 peanuts. And here it comes. It says 9 times 5 is equal to 45 peanuts. Let us try to interpret this number operation further. What does 9 represent in this case? 9 represents how many peanuts in one box or one group. Permit me to call this either a box or a group. So 9 represents how many peanuts in a box. So 9 peanuts per box, that is 9 peanuts for every box. Then times 5. What does 5 represent? How many boxes? We have 1, 2, 3, 4, 5 boxes. There are 9 peanuts in a box times how many boxes? 5. That is what we mean by saying 9 peanuts per box times 5 boxes, and that will give us 45 peanuts. This is not the only way to arrange these 45 peanuts. We have many other ways we can arrange these 45 peanuts in groups. It is never compulsory that there must be 9 peanuts in a group. We can have even 2 peanuts in a group. We can even make 1 peanut as a group. That is going to be a special case afterwards. But just bear in mind that the fact that we have 9 in a box does not mean that just for simplicity. So I repeat that there are many other ways we can group these 45 peanuts. But let's just continue with these 9 peanuts per box. Now back to what we were saying before, we said that 9 peanuts per box times 5 boxes is equal to 45. In brief, 9 times 5 is equal to 45. The question is 9 counting how many 5s? Or is 5 counting how many 9s? Let us go back to our boxes. 9, 9, 9, 9, 9. That is 5 9s. 5 9s. If I say 5 9s, which one is counting which? Obviously, from the statement, 5 is counting how many 9s that we have. Let me write 5 9s in a simpler way. Here we have it. The expression 9 times 5 is also written as 5 times 9. A lot of commutation empowers us to write 9 times 5 as 5 times 9. I believe that later you will learn a lot of commutation under the topic known as the arithmetic laws. But until then, the preview is that when two numbers or more are multiplying or adding, the arrangement does not matter because the answer is always the same. If you bring 9 into 5 times, the answer is 45. And if you bring 5 into 9 times, the answer is still 45. It thinks, therefore, that 9 times 5 and 5 times 9 commutatively are the same and correct. Therefore, we choose the second option, 5 times 9 or 5 9s. In fact, it is this 9 times 5 that is actually shown to be 5 9s. It is not this that became this, it is this that became this one. If you say 9 times 5, it means the same thing as 5 9s. And so when pronounced, see it here, 5 9s. The implication is that this multiplication here, 9 times 5 is equal to 45, means that 5 9s, that is 5 bracket 9, is equal to 45. This expression, 5 9s is equal to 45, shows that numbers can count numbers. For some time now, you may have been thinking that numbers only count items. For instance, somebody can say 5 books. If you say 5 books, the 5 is counting how many books, but book is an item and 5 is a number. In this case, we have 5 9s. The two things involved are numbers. 5 is a number and 9 is also a number. So a number is counting a number. Now, from this point on, just know that this concept of number counting numbers will feature every time throughout the time we consider the fundamentals of algebra. Already, I have given the preview of the roles played by 5 and 9, but it is important that we give time to explain clearly the role of 5 and that of 9 in this expression. 5 9s is equal to 45. Let us see. In this expression, 5 9s, 5, that is this 5, counts how many 9s. This 5 is telling us how many 9s we have. We have 5 9s. Right? Then the number being counted is called countee, while the one counting is called the coefficient or counter. So of these two, which one is counting which? We've known that 5 is counting 9. Because of that, the countee in this expression is 9 and the coefficient is 5. don't forget that the county is start being counted, and then the coefficient or counter is start, which is counting. We therefore conclude that in this expression of 5 bracket 9, that is 5 ninths, the coefficient of 9 is 5. What lesson have we learned so far? Among other lessons we have learned, one thing stands out. What is it? Instead of counting things one by one, we can choose to count them in groups. We just counted 45 in 5 groups, each containing 9 peanuts. That was beautiful and short, very brief indeed. Now, what happens if the number in each group changes from 9 to something different? It is not compulsory that the number of peanuts in each box is equal to 9. If there is a change in number of peanuts in this group, the same change should reflect in all the 5 groups. Now, let there be 10 peanuts in each group, so that I add 1 dot each to all the 5 groups. Let us see what the answer turns out to be, but certainly you wouldn't expect the answer to be equal to 45 again. But one thing we have known is that we can avoid counting things one by one. Instead, we can count things by grouping and by multiplication, as the case may be. And here comes that challenge. Please carefully count how many peanuts that are now in each group. Are they still 9? Just count all of them. There is one difference between what used to be and what is now. I think at this point in time we have the 10th dot in all the boxes. What it means is that each box now contains 10 peanuts. If you count them one by one, will you still get 45? The answer is no. Because we have known that it is easier and better to use bundles or groups to count items, we're going to adopt that to count how many peanuts we now have in these 5 groups altogether. What will it be? Will it still be 9 times 5? Certainly no. It is now going to be 10 times 5. Let us see how many peanuts we're going to have now that we have the 10th peanut in each group. Please watch out. And here it comes. Now that we have 10 peanuts in each box, we now have 10 times 5 is equal to 50. We can also say 5 tenths is equal to 50. In this case, the county is 10 and the coefficient is 5. So 5 is counting how many tenths we have. Altogether, we have 50 peanuts. Now, let me wipe off 2 peanuts from each group and let us see the total number of peanuts in all the 5 groups. Let that happen. And here it comes. How many peanuts are in each box? Do we still have them as 10? The answer is no. Are they still 9? The answer is no. If you watch carefully and count carefully, you observe that each box now contains 8 peanuts. What it thinks is that we have 8 here, 8 here, 8 here, 8 here, 8 here. To help bypass the counting by units, that is counting each peanut differently, let us count in bundles or count in groups, which is better, saves time and energy. So what do we do to get the number of peanuts across all these 5 groups? It is now going to be 8 times 5. Let us see. And here it is. It is now 8 times 5 is equal to 40, meaning 5 eighths. 5 eighths is equal to 40. That is 8 brought into 5 times is equal to 40. So in this case, What is the county and what is the coefficient? Obviously, the county is 8 and the coefficient is 5, and the answer is equal to 40 peanuts. So bypassing counting the peanuts one by one, we have known how many peanuts we have in this easy way. Already, we are enjoying the benefits of counting items in groups. Let's continue removing one peanut each time. I want to remove one peanut from each of them, and let's see how many peanuts in all. Let it happen. Now, what are you seeing? Each box now contains how many? 7 peanuts. Confirm that each box now contains 7 peanuts. So how many peanuts do we now have in all of them, in all the boxes? Already, the pattern is to use groups to get that total. What will it be? It will be 7 times 5. Let's see what it turns out to be. And here it comes. It is 7 times 5. 7 peanuts times 7 boxes. That is 5 sevens is equal to 35 peanuts. We ask again in like manner, which one is the counter? That is the coefficient. And which one is the county? That is the one being counted. If you remember what I said earlier, not hesitate to say that 7 is the county and 5 is the coefficient. Alright, let me again remove one peanut from each box. Let us see how many peanuts in all. And here the change has been effected. In each box, how many peanuts do we have? Obviously, we have 6 peanuts in each box. So what do we do to get the number of peanuts across all the boxes? I'm sure that the trend is getting more and more accustomed to. That means you can tell ahead of time what number of peanuts there will be if we have 6 peanuts per box. What will it be? It will equal to 6 times 5. And here it is. 6 times 5 is equal to 30 peanuts in all of them. That is 5 sixes. 5 sixes. That is 6 into 5 is this expression. So in this expression, which one is the county and which one is the coefficient? Obviously, 6 is the county and 5 is its coefficient. Alright, you can imagine what will happen if we keep on removing one peanut each until we have just one peanut inside. If we have one peanut inside, we can now say 1 times 5. 1 times 5. Let us see what will happen if at the end we have one peanut each in the box or in all the boxes. I bypass all the steps of removing one extra peanut until we get to one peanut. So I want to run straight to having one peanut inside each box, believing that you know that we can still remove one peanut one after the other until we have only one remaining in each box. Straight away, let there be one peanut inside each box. And here we have one peanut in each box. In like manner, what do we do to get the number of peanuts across the 5 boxes? You may ask, is it still necessary to do that? The answer is yes. Are you asking that because it has become a lot easier to know how many peanuts in all of them? That's because just one box contains one peanut. That will not be the reason why we have to abandon the pattern we have adopted and have been using to this point. With that pattern, how do you get the number of peanuts across the 5 boxes? It is going to equal to 1 peanut times 5 boxes. Let me write it. And here we have it. 1 times 5 is equal to 5. In brief, we say 5 ones. 5 ones is equal to 5. That is 1, 1 brought into 5 times. 1, 1, 1 brought into 5 times. This is what this summary is telling us. What it means is that we can have 1 peanut, 2 peanuts, 3 peanuts, 4 peanuts, 5 peanuts. Just any number of peanuts in this box. But because we have 5 boxes here, each of them will have 5 counting. So the implication is that the number of boxes is constant, that is 5, but the number in the box is not constant. If you have been following from the start to this point, you must have noticed that we had different numbers of peanuts in each box. To this point of having 1, we had even up to 10. Then from 10, the first was 9, then 10, we had 8, 7, 6, down to now 1. What it means is that the number in the box can change, but because we have 5 boxes, we still say 5 times how many in the box. Let me summarize all the number operations we have carried out, or we ought to have carried out, with the numbers of peanuts changing across all the 5 boxes. Let the summary come. And here comes the summary. It says like this: 5 times 10, that is 5 tens is 50. When there were 10 peanuts in a box, we had 5 tens give us 50 peanuts in all. Next, we had 9 peanuts. The first was 9 peanuts anyway. 10 peanuts came later. But in this arrangement, the 5 tens comes first. Whichever way, we had all of them that feature in this summary. So we have 5 tens, and that gave us 45 peanuts. 5 eights, we had 40 peanuts. When there were 7 peanuts in a box, we had 5 sevens. And not in all, we had 35 peanuts. When there were 6 peanuts in a box, we have 5 sixes. And altogether, we had 30 peanuts. In that order, until we had only 1 peanut remaining in each box. And at this time, we had 5 ones, and that gave us 5 peanuts. I wish to stress the lessons we have learned so far. The first I want to remember is that instead of counting items one by one that takes time and energy, we can choose to count the items in groups of equal number. Second lesson that stands out is that with these number operations that have been going on, we come to the conclusion that numbers don't just count items. Numbers count numbers. Imagine 5 counting how many tens, 5 counting how many nines, 5 counting how many eights, 5 counting how many sevens, 5 counting how many sixes, and 5 counting how many ones. That does not mean that in every case, 5 is the counter in everything we do. 5 is used only because in our case, we have 5 boxes. If we had had 7 boxes, 7 would have been the counter and other numbers countees. It is very important to note that these brackets are necessary when numbers count numbers, and each number, both the counter and the countee, are clear constants. 10 is a constant and 5 is a constant. 5 is a constant and 9 is a constant. 5 is counting 9 and 5 is counting 10 here. Also, 5 is a constant and 8 is a constant in that manner. If we don't include these brackets to show that 5 is counting 10 or 5 is counting 9 or 5 is counting 8, just imagine what will happen if each of these brackets is removed. Please, what will it be like if this bracket is removed? Just imagine that this bracket is removed. It will equal to 510. If you take this bracket out, the thing will be called 59, no longer 5 nines. If you take this bracket off, it will now be sounding like, or it will now be 58, and this will be 57, and this will be 56, and this will be 51. But because we have brackets in each of them, it has become clear that this is not 510, but 5 tens. And this is not 59, but 5 nines. And this is not 58, but 5 eights, in that order. Let us see an aspect that to make us think deeply about an emerging challenge of counting what you don't know. Let us assume that you don't know how many peanuts in a box. You only know that the box contains peanuts. That we showed the number of peanuts in the box. It's just for a start and for us to get the glimpse of the challenge that will come afterwards when we are not told how many in the box, but we simply know that there is a box containing peanuts. That we had 10, 9, 8, 7, 6, down to 1 peanuts each in each box does not mean that we are always sure of how many peanuts. After all, if the box is wrapped or closed, all you see is a box. You don't know how many peanuts are inside the box. If there are 10, then we have 50. If there are 9, we have 45 in all. If there are 8 peanuts, then all the 5 boxes will give us 40 peanuts. If there are 7 in each box, then the 5 boxes will give us 35 peanuts. The fact that the number of peanuts in each box can change from 10 to 9 to 8 to 7 to 6 and down to 1 is a challenge. The implication is that when the number of the peanuts in each box is not known, it will become practically impossible to tell how many peanuts across all the 5 boxes. These numbers that keep on changing from 10 to 9 to 8, 7, 6 down to 1, for instance, which do not remain constant, are called variables. That is, the number in each box is not constant. The number can change. Because that number can change, a number that can change from one value to the other is called variable. Let me write that. See it here. A variable is a number having a value that can change. Put simply, a changing number or a changeable number is called a variable. Which ones here do you refer to as variables? We know that once 10 is fixed here, 10 becomes a constant. But if we don't know how many that are in that box, that number, which we don't know, which can take any value at all, is a variable. See it. It can take the value of 10, 9, 8, 7. It thinks that the number in this box has a value that can become 10, that can become 9, that can become 8, that can become 7, 6, down to 1. Because of that, the number in this box is a variable. Notice again that in each of these expressions, the counter is known and the countee is also known. And that is why the answer at the end is very clear. 50, 45, 40, 35, 30, then down to 5. What if something happens to this countee? What thing happens to countee? That is, if a countee turns to a variable. For instance, if this 10 turns to a variable, that is, if we now are no longer sure of how many peanuts in a box, can we still say 50? The answer is no. These answers are clearly stated because the counters, that is the coefficients, and the countees are known. A type of mathematics in which both the counter and the countee are known is called arithmetic. But something will soon happen when something happens to either the counter or the countee. That is, when one of them turns to a variable. In the case that we're handling, it is the countee that likely will take forms of variables because the numbers in the boxes have changed from 10 to 9 to 8, even down to 1. Therefore, let this countee not be known. What if I come here and say, I don't know if there are 10 peanuts in this box. Let me use letter of alphabet to represent each of these numbers. I don't know whether there are 10 of them, but let it be that there are C peanuts. Let C represent the number of peanuts in this case. What then will it be? Let us see. We say it here, 5C. If you say 5C, can you comfortably say that the answer is equal to 50? No. The reason is that you don't know if C is 10. C can be something more than 10 or less than 10. But because you don't know it, C has become a variable. So when I have 5 bracket C, that is 5 C's, we cannot say that we have 50 peanuts in all of them. Because of that, that 50 must vanish. And here it comes. This 5C can't comfortably or surely become 50 because we don't know what C is. So this 5 bracket C or 5 C's, if you don't want to write it in this way, it can be written in this way. Which of these two appearances of 5C do you prefer? On my own part, I prefer it this way. That is because if you write 5C without the bracket, nobody will be tempted to call it a particular constant number, unlike before. Like this one, if you don't write brackets to enclose this 9, without this bracket, somebody will call it 59. But if it is the alphabet that is here, the bracket can be dropped. I say can, not must be dropped. If we drop it, it becomes simpler in writing. Again, this 5 bracket C has become 5C. At this point, the coefficient is still known, but the countee has become unknown. A new form of mathematics is creeping in gradually. A different type of mathematics, a special type of number operation, is developing gradually. Remember that if the counter and the countee are known, the part of mathematics concerned is called arithmetic. But now the counter is known, the countee unknown. We should not call this 5C pure arithmetic. Instead, at this point in time, it is going to put on a new name. But before then, let us do the similar thing to the remaining number operations. Let me remove this 9 and replace it with a letter of alphabet in like manner. This 8, this 7, this 6, and this 1 will experience a similar thing. Please permit me to remove all these numbers and replace them with letters of alphabets. Please watch out. And here they come: 5B, 5G, 5X, 5Y, and 5Z. At this point, are we still going to be correct if we say that 5B is equal to 45? No. Only in the cases of the equation where we have to solve and get the value of B for which this statement is correct. We are not supposed to write 45 as the answer to 5b. This 45 will stay when there were 9 peanuts in this box. But where the number goes beyond 9 to unknown number, that unknown number has become b. So we're going to wipe off all these numbers, which have their roots to the time we dealt with pure arithmetic. At this point in time, let them go away. I will write this in the manner of this first instance. And here they come. 5c, or this just 5, this 5c, 5 bracket b, or just 5b, 5 bracket g, or just 5g, 5 bracket x, or just 5x, 5 bracket y, or just 5y, 5 bracket z, or just 5z. In summary, if this C represents number of peanuts in this box, C tells us that we don't know how many peanuts in a box, but there are 5 boxes. So the coefficient 5 is known, but the countee, which is number of peanuts in this box, is unknown. Also, the B means that we don't know how many peanuts in a box, and we have 5 boxes. All we can count is how many boxes, but not number of peanuts. The implication is that we cannot progress to the point of telling how many peanuts in all the boxes. We can only count the boxes. Like I said earlier, a new type of mathematics is emerging gradually. A type of mathematics in which somebody counts how many bundles, how many groups, but cannot tell how many items. Again, if G represents the number of peanuts in this box, and 5 says we have 5 boxes of such, same thing applicable to this 5x, 5y, and 5z. So the C, the B, the G, the x, y, z are all examples of variables. When a variable comes into mathematical operation, it becomes impossible to tell exactly the number of items being counted. All we can do is to count how many groups of such items. Therefore, we have come to a branch of mathematics in which we cannot tell the exact number. Instead, we can tell the exact number of groups of numbers. In other words, the counters or coefficients are known, but the countees are variables. This aspect of mathematics, this new branch of mathematics, that this allows us to get the exact number of items being counted in such a way that what is being counted is unknown, but what is counting is known. That is, countees are unknown, but counters are known. It's called algebra. Again, algebra. So what is algebra? Let me define it. And here it comes. It says algebra is arithmetic of variables. This is a simple definition, but it is packed with information. Already, you know what is called arithmetic, and shortly after that, just in this presentation, I mentioned the meaning of variables. A number whose value can change is a variable. So arithmetic is the process of adding, subtracting, multiplying, and dividing. It therefore means that algebra, when defined differently, is a branch of mathematics that deals with addition, subtraction, multiplication, and division of variables. In our case that we have been handling, it has always been multiplication. That does not mean that it is only multiplication that we can carry out with variables. After all, 5c when interpreted will give us addition. 5b when interpreted will also give us addition. In fact, let me rewrite each of these expressions in their different ways. But before then, let me stress again that in algebra, when counting items, we don't get the exact number of items. We only tell how many groups of such items. We get the number of such items only when we are told the exact number in one group. But until then, the number in each group is unknown and is therefore called a variable. Each of these letters of alphabets represents a number. But as long as that number is unknown, this is as far as we can go. We could not go beyond this. We can't go beyond this to give an exact number since C is not known. We can't give a number to this since B is not known. We can't give a constant number to 5G since G is not known. We cannot give a constant number to this since X is not known. In like manner, 5Y and 5Z. Let me write each of these expressions to reflect addition. And here they come. Alternatively, 5C actually means C plus C plus C plus C plus C. And 5B means B plus B plus B plus B plus B. And 5G means G plus G plus G plus G plus G. In that manner, applicable to X, Y, and Z. So here we are multiplying 5 by C, and here we are adding the C's. In other words, it is not only multiplication we can carry out with variables. This is just a case in point, and so far we've been able to see how we can multiply and how we can add numbers, and those numbers are not known and they are called variables. Since it is possible to multiply and add variables, we can also conceive it in our hearts and believe that it is possible to subtract and divide using variables. So the process of adding, subtracting, multiplying, and dividing with variables is what we refer to algebra. This is a branch of mathematics of its own. In it, we don't get the exact numbers. Instead, we get numbers of groups. I repeat, in algebra, we don't get exact numbers, but we get numbers of groups, or the number of numbers per group. Except we are told the number in a group, we cannot get the exact number. That unknown number is what we refer to as a variable, and the arithmetic of all of variables is what we refer to as algebra. With the following simple exercise, check if you have been following what I've been saying. And here comes a very simple but very important challenge. It says, if 5 bracket 9 means 5 nines, interpret and evaluate. It means you interpret these expressions, and after interpreting each of them, you evaluate. That is, tell the answer. So if 5 bracket 9 means 5 nines, then interpret and evaluate 1, 9 bracket 5, 2, 3 bracket 4, 3, 6 bracket 7, 4, 10 bracket 2, number 5, 7 bracket 7, and number 6, 8 bracket 5.